Welcome to the Electric Goddess podcast. Thanks for tuning in. Today we're talking about corrosion, and this is a topic that Luke is very familiar with due to some hard lessons, and we're really excited to be talking with you about a subject that not many people in the battery industry are talking about yet. And so while we call these podcast intros, basic battery knowledge is suggested to get the most out of our podcasts. The first question today is, how does corrosion happen so quickly in batteries?
Corrosion can be driven from a number of effects, ranging from erosion to chemical bonding and consumption, conversion to soluble compounds. And in this case, a special kind of erosion is vulnerable to batteries in that there is voltage gradients between many conductive surfaces in the battery. If we think about some causes of corrosion, maybe you've heard of galvanic corrosion issues, in which case you have some dissimilar metal interface with an electrolyte, and as a result of that there's a voltage produced proportional to the difference in their galvanic series potentials. And this is essentially an unintentional battery in this case, driving them to occur not only much more rapidly, but to a completion and to a state of chemistry that wouldn't have been possible without the voltage present to provide the energy to drive the reaction.
What do you mean by a completion of corrosion?
I mean, corrosion will affect anything with a voltage gradient on it in an electrolyte that conducts. And so completion of corrosion means you've either removed through transformation of salts through electrolysis, dissolving it one little bit at a time until there's no conductive metal surfaces left to be wetted and sustain that gradient to drive current and continue the process. Or completion can be passivation. Some materials grow a layer that resists further conduction as they corrode. Classics being titanium, aluminum to a lesser extent in the right pH of solutions. And these allow corrosion to persist until loss of conductivity on the electrode rather than loss of conductive material mass from the electrode. When I say electrode, it could be a piece of your bus bar, it could be the wires between the backs of a plug and a harness, it could be a wetted trace on a circuit board. Any of these things become the electrode when you add an electrolyte that allows the electrolysis process to begin.
So what are some methods of identifying corrosion?
Of course, the elephant in the room would be, do you see some significant self-discharge difference in a string? And if so, one of the mechanisms that can be is a corrosive trail that it's asymmetrically causing current in your battery assembly to cause one string to drop. Now that's one of the more gentle mechanisms, though. The more serious mechanisms of corrosion are when you see a chassis isolation fault to somewhere mid-string, meaning that whether it's an ionic current path or a resistive current path, usually an ionic current path. So the chassis isolation testing value is critical for finding the more serious forms of isolation faults. When the value is in a higher resistance range, say over 5 to 10K ohms, 5 to 10,000 ohms, these paths generally are ionic through some liquid electrolyte. It's common to see them all the way up to the say 500 kilo ohm range. Signatures for an ionic path, to identify it further. Obviously, you can track whether that chassis resistance tracks up or down, and in situations where you know that the vehicle may have just had an extreme water exposure and now it's in a dry environment, sometimes you'll see that track increasing in resistance until that fault reduces. However, unfortunately, in more situations, you see those faults continue to reinforce the residual salt trail. So whenever the electrolyte is bridging places that are at a different voltage potential and you exceed the dissociation potential for that metal, again, this is only a volt or two. For, the toughest metals, gold, platinum, iridium, tantalum, can buy you something like 4 volts or so. But it depends on the electrolyte, complicated, but pH of the solution as well.
Why is protection from corrosion important? Like, why are we making a podcast on this?
The short answer is because recalls are expensive and ruin a business case from working. And the alternative to recalls, shipping an unsafe product and having it burn, is also a non-sustainable business case. And so this is why corrosion is so critically important. What I was getting into with the metal platings is, with any metal surface plating that you're running, be it gold, be it tantalum, platinum, these metals can only buy you a couple volts of dissociation potential before they are also dissolved into your electrolyte solution, which may just be, condensates of dew for your electrolyte solution. This is why you must break the path for that conduction to occur across the electrolyte. It's critical that you don't have capillary wicking paths that can bridge any points in the assembly, or they will be consumed by electricity. Dew at a conceptual level, like condensates from the humidity that you see on blades of grass in your lawn. You might think, this doesn't have ionic conduction potential because it's pure water, it's deionized. But being in the atmosphere at 400 parts per million carbon dioxide means it dissolves the partial pressure in of CO2, forming carbonic acid, which is a ready ion conductor for the materials in a battery, including copper, aluminum, iron. And for this reason, whenever we apply more than just a couple of volts of difference across a cohesive liquid path between voltage gradient points, we are pulling material from one side being consumed as an anode, dissolving salts into this solution. And as we dissolve metal salts, initially starting with just carbonic acid as our ionic conductor, but as we begin to dissolve metal salts, we leave a downward trending resistance curve with improved ionic solubility. So this is a positive feedback loop to be able to pull more ions with additional current flow as the solution becomes more saturated. This is part of the risk that leads to a molten salt bridge occurring, but also leads to loss of critical interconnect and conductive pathway infrastructure, which can also lead to a fire from inadequate cross-section or high resistance contacts.
There's the larger question of, what is the chemistry makeup of corrosion?
So the makeup of corrosion depends slightly on what was driving the corrosion mechanic. I say this because if it's road salt spray, it'll be loaded with chlorides and sulfates, which are able to form mini low melting point ionic salts in their hydrate forms, which can bridge, leading to a molten salt bridge and a fire.
I guess we have that article that we wrote, which kind of went on all the different chemical makeups for those that are really interested on diving deep on that. Yep. Rather than listing it off.
Yeah, we have an article. I could start going through ions and cations with you, but we have an article that describes which sources of the salts are endemic. And what I mean by that is you only need atmosphere to produce these compounds. So this includes carbonates, carbonates of copper, carbonates of aluminum, carbonates of iron. And this requires, only changes in dew point shift in your pack. So merely by changing temperature, humidity profiles in your pack, you can produce all of these types of salts. And then we have the if road salt fog was a factor. When vehicles drive on salted roads, their wheels stream little droplets off the shear layer that was wetting the road off the rubber, and these little sheared droplets have a small radius, just a handful of microns in diameter, and are loaded with the chloride salts, sulfate salts, both with magnesium ions, potassium ions, sodium ions, aluminum ions. And this is because road salt blends, unlike what the salt fog standards would suggest you run to validate your vehicle, the road salt blends are not high purity sodium chloride. They are the cheapest salt they can mine dump truck loads of, unpurified. And this is why you can form these significant differences in corrosion behavior in a test when you run representative road salt mixtures in battery tests, as opposed to running the by the book standard, which gives you false positives to think you have no problem when you do.
I think that's why you became one of the leading experts in battery corrosion, is because people do weird stuff to their batteries, right? They salt the roads, they power wash their bikes, they lose their motorcycles in the surf,
They power wash their cars and Ford Rivers with them unsuccessfully and drive out in the surf with their cars and all kinds of things too. Yep. But those things are the extreme outliers. The wolf in sheep's clothing is merely commuting in situations where either the roads are salted or you have the right daytime temperature, daytime humidity, nighttime temperature, nighttime dew point cycle. And in these situations, even if the user just has the vehicle parked in front of their house, never even turning it on to use it, the vehicle runs this humidity pump cycle where they will, every day as the solar gain that had warmed the pack cools down, they will ingress humidity. And if that time of ingressing humidity happens to coincide with peak saturated dew point for that location at the time, shortly after sunset, then they will run a one-way condensate trap to continue to accumulate a mass of liquid water condensates in the battery.
I recently read an article that there's no clean dew or rainwater on Earth, but just assuming that there was that and there's no chemical reaction happening.
The good news is those articles that were talking about PFOAs, that would help your battery more than hurt it. That's a really corrosion resilient compound to be in the water with it.
And we visited a really cool ag tech robot company in Seattle, and they were talking about pesticides on the farm. So let's say if they're in the middle of the US, lots of great farmers, they don't necessarily have salt on their roads because they're not big cities.
Yeah, but they spray a mist of nitrates and phosphates and sulfates as a fertilizer. And even the dust from dried crystals on crop fields, as the dust blows across the road and their cars drive through the dust, it's only a matter of needing the right humidity conditions to form these other sources of nitrates and phosphates into a corrosion problem, or worst case, your corrosion problem. I used to think the worst case in a corrosion problem was that the device stopped working, but that's actually the best case in a corrosion problem. The worst case in a corrosion problem is you form a molten salt bridge and it doesn't die gracefully. It incinerates in a fiery plasma.
So corrosion, does it vary based on use case? I mean, we have stationary storage batteries being put out there. You have bicycles, motorcycles, automotives, a lot of stuff we've been talking about, buses, aircrafts.
I think that first point you mentioned on stationary storage is a perfect example of how diverse corrosion can be and the challenges that you deal with can be. I came from a data center background, and in this situation, our stationary storage was in temperature and humidity climate controlled facilities. After commissioning, they never saw vibration. They were bolted to concrete. They never saw temp fluctuation or dew or condensation or road spray.
So pampered.
Yeah, so they had a very ideal environment in a data center environment. However, the same label of application of grid storage battery could be put in use in a situation where it's just a little shed with no climate control in a very rough tropical environment or high dew point condensation environment, in which case, every day it deals with condensates, and if it's near the ocean, it might have corrosive salt sprays and condensates. And this is how wide the range of protection needs depending on the application may be.
So you're saying we should still be paranoid about corrosion even if you have like a cube stationary storage that has like an AC that runs?
If you're climate controlling your dew point from ever forming a liquid condensate, then you should be free of the electrolyte path to begin this advanced corrosion, this rapid electrolysis driven corrosion that batteries can support. And so provided your environmental controls are sound, you can pull off a system like that. But there's considerations like you've got to be able to ship this system and maybe even move the system from its location 1 to location 2.
So even with stationary storage, especially ones that are outside,
That's right.
there's a corrosion risk.
Yep. And if you were in the right location, even in your garage could be a big problem. There's garages where every tool in it is uncorroded and rust free, and there's people's garages where everything is rapidly rusted, and it depends a lot on the climate and humidity and environment and airflow and many factors as to how corrosive that environment will be, even of a home garage.
What kind of corrosion risks are there for e-bikes or electric motorcycles?
Drastic corrosion risks. I think they're some of the most challenging of all the battery topologies to make rugged and reliable for a long service life, for the reasons being that
They just abused?
they have no body work in general to protect them from the direct tire spray, so that the wheels are constantly creating a mist that the battery is passing through, in a turbulent mist of whatever liquid conditions were on the ground, sometimes salty, sometimes less salty. But these droplets, this fog that swirls through the product constantly, is very challenging for corrosion, kind of like running a continuous salt fog test depending on the application in like New York in winter, salted roads. However, so these salted road conditions are particularly challenging for two-wheeled vehicles for the aforementioned reasons, but also because these profiles have very high shock and vibration, so that relative surface interfaces on sealing, enclosure halves, geometry constrainment and control of the geometry of sealing interfaces in an application that is subjected to high G-force impacts and shock and vibration, and being left in the sun, being left in snowbanks. These all build significant challenges that in many ways full-scale automotive batteries have less challenges, but at the same time they're dealing with lower currents, lower power, and lower voltages, and so that side of the pack designs are all
Like they might have a higher chance of dying gracefully?
I was just saying, from a design difficulty perspective, at least your interconnect architecture and busing is very easy on those packs, because the usage case for vibration, for corrosion, is very aggressive, and so at least I get one easy column to check.
There's a lot of movement on high voltage, heavy duty vehicles. So, we want an electric semi truck. Mm-hmm. We're waiting for that. There's also a lot of electric buses coming out, like giant fleets being put out. Do you see that being different from
Yes.
a risk point of view than automotives?
That actually brings up non-electrolysis-based corrosion. So this is dielectric decay and dielectric decay through ionic migration. And this is where you simply maintain an electrostatic field gradient across your dielectric, and the dielectric's properties degrade. For most dielectric insulator materials, it happens much faster, sometimes many orders of magnitude faster when they're saturated with humidity relative to when they've just been injection molded and are a dry part. This is, I think it's a formidable challenge in industry right now that is both underlooked at and under-addressed and under-validated. The reason being, most industry standards and specifications today call out a high pot as their dielectric strength measurement or qualification of minimum dielectric strength with a high pot. The trouble here is that because the test is over in 30 seconds to a minute, or say it's a withstand for 5 minutes or something, because of this time constant of the measurement, it can't quantify your degradation of your dielectric strength. Dielectric degradation is a time over electrostatic field gradient stress process, and when it's ionic migration related, then it's also related to the base metals at each side, one side serving as an anode to pull metal ions drive through the polymer. You may be thinking, well, how can it do this with an electrostatic field and no current path? But remember, all dielectrics, even when you measure your resistance on a dielectric and it says it's 500 megaohms or something, even 500 megaohms with even 1 volt of difference across it still flows millions of electrons per second. And it's these millions of electrons per second that are driving the, you could say, thermokinetic ionic ping pong of the surface ions that are being driven through that material. The reason why it's a problem is because the materials bonds scissor and split, and their polymer degrades its lengths as it transports these materials across it, eventually reaching the point of becoming, there's a couple of outcomes as it progresses. One is that it becomes chaining down in resistance, trending down in resistance until the point that it goes thermal. And the other path is that it becomes mechanically fractured and crazed to the point that it crumbles apart and loses mechanical integrity of the purpose of the part's function. And so it's critical to, when you're doing high voltage systems, to evaluate the stress on each of the components. You might think, well, how much stress can, say 400 to 800 volts be on something? But, when you're dealing with a system at, say, 600 to 800 volts, any sharp breakout point that can focus the electrostatic field.
This is like defects in coatings, like an adhesive not applied correctly.
A crimped joint that has a tiny wire whisker poking off to the side. Anything that allows you could say an electrostatic field stress riser concentration point or focusing point. But wherever you have these focusing points, you'll actually see the air. You'll see, the spectral emissions colors of diatomic oxygen and diatomic nitrogen splitting from this field stress. And so if, you have to be in a dark room looking very carefully with your eyes adjusted well, and you'll actually see the, spectral emissions of generating plasma from the field strength. And this is the same stress that will split the air is the stress you're putting through your polymer dielectrics continuously. And this is why, this is the difference between the high pot, which says, I imposed this significant magnitude of electrostatic field stress for some brief interval, and it didn't spontaneously avalanche into a conductive breakdown of electron flow. and that's what you validated, but that really validates nothing at all to do with whether it survives long-term under DC gradients. There's a lot of insulator material with a lot of data for them being used in high voltage where it's AC, and AC always has an equal and opposite ionic migration effect, so that you have a net zero dielectric ionic migration gradient, a net zero cause for the dominant source of this dielectric decay. And this is why many insulators, say there's certain ceramics that work great with AC. If you impose a similar voltage of DC or even less DC, you'll find they migrate metal ions through them, and you'll see the ceramic discolor locally from this migration effect. Ceramics do it with a really slow time constant, but unfortunately polymeric materials do it with the proportionately faster thermal kinetic of their structure.
It seems like we always come back to high voltage warnings, or I always think about...
It's one type of corrosion to discuss in a battery,
right,
is dielectric decay effects from electrostatic field. And the other type that we discussed earlier is the very rapid one. So
molten salt bridge.
Yeah, forming the molten salt bridge and quickly consuming through electrolysis large volumes of metal, forming salt paths. This process happens to...
So voltage exasperates it.
Yeah, that process will happen with a scooter battery, or an 800 volt battery. But the dielectric decay effects, which are long-term effects, rarely would you see decomposition to failure in, say, 1 year or perhaps even 2 years with those effects. But they're no less important of something to validate if it means in 3 or 4 years all of your products fail dangerously, right? So this is why it's critical to...
There's so many manufacturing risks you're taking, especially with corrosion.
That's right.
And
that's why we run
decay.
So many validation tests to try to reduce those risks.
I wanted to talk a little bit about aircrafts, but I think we kind of got into it with at least ground transportation corrosion, because I think aircrafts is a bit different.
Aircraft has a special corrosion concern I'll briefly mention. Because of the cruising altitude, barometric pressure difference, and temperature difference between ground, they run a very large swing, a very large delta P and a very large delta T. And your delta P and T are what allow you to run your humidity pump if you have an enclosed volume that has any pinhole weepage. So if you don't have a perfect hermetic, vapor-tight, gas-tight seal, then aircraft have a really aggressive swing in their pump displacement, you could say, for driving humidity to ingress and accumulate.
So how does one protect their battery from corrosion?
If money is no object and weight and volume are your most precious metrics, you can use something they often use for pacemakers and medical implants called Parylene. I usually like Parylene C, but it's a xylene dimer that you gas deposit, and it chem absorbs 1/2 chain length or 1 xylene dimer thickness, so that it doesn't accumulate more than a certain defined thickness of microns over your part. And it's very chemically resilient and effective as a solution for corrosion problems, but also from a cost perspective, it is totally off the table for automotive and many other environments. So that leads you to solutions like potting.
You say it like it's all like you're scared to say it.
Well, I say it this way because people hate the idea of adding weight and volume to their battery when the gravimetrics are so precious in watt-hours per kilogram, watt-hours per liter. However, when you consider your other option is maintaining a hermetic seal over the life of the product, the reason it's infeasible to not pot for automotive is because you can do things like helium leak down test to ensure you've got a hermetic seal on each pack that left your factory, but you can't guarantee over the life of the vehicle, the things that it impacts on the road even just hitting a tall speed bump,
Someone touching it.
yeah, that you didn't lose your hermetic seal over the life of the product. Even just thermal expansion, contraction stress, or asymmetry of temperature, can cause internal surface-to-surface interface stress to lose these gas tight seals. And so,
Kind of like we've seen some videos of like old canned foods, like some of them make it and some of them don't.
yeah, it's a lot like that actually. And you don't know if that's nature or nurture when the canned foods that make it, it could have been that they were all perfect from the factory, but some of them were handled slightly more roughly than others on seals, and that's why they failed. And it could have been factory lack of sealing too. If it's just canned food, I'm sure nobody's helium leak down testing it.
I don't know. Okay, so what tests should be run during the design phase? I know we could talk forever on potting and why it's the best, but maybe just in general, if you decide that you don't want your cells closer together, you don't want thermal protection, the extra, or thermal runaway protection, the extra stuff that potting gives when you add it to a battery design.
The reasons why people end up going to potting is because even though you might have some engineers that can make a hermetically sealed pack a couple of times, ensuring that seal lasts is quite the tall order. And from a manufacturability perspective, the repeatability of the potting is amazing. The formulations that we use are just thick enough to keep their endothermic fillers laden in suspension. So there's just enough fumed silica so that they'll maintain solids distribution uniformly, but still degas quickly when poured into an assembly. This is one of the critical elements in why potting is so effective is its manufacturability to reliably and completely monolithically encapsulate from corrosion and humidity ingress on assemblies that the surface area and the perimeter area, of all the bounded structures in a say it's a module of cells, is impractical to encapsulate in a manufacturing-friendly, repeatable, and durable method through other means.
And kind of to bring back some of the voltage stuff you were talking about earlier, does potting help with, let's say you have a manufacturing defect with like that one little copper strand hanging out, or? The
dielectric strength of the potting is much higher than the strength of the air, orders of magnitude higher, and so when you have those electrostatic field defects, you'll have one further layer of protection
from degradation.
Yeah, from becoming an impending degradation problem. One of the biggest advantages of potting, of course, is I mentioned a tiny bit about the endothermic fillers, but those endothermic filler solids, don't be confused with thinking of a phase change like wax melting, for example. This is a one-time chemical bond cracking, and it absorbs over 100x the energy per its volume of wax melting. But it's also only functions one time to absorb this tremendous energy spike. Fortunately, from a battery perspective, this is what you need to pass thermal runaway, is the absorption of one tremendous spike of thermal energy without the cells adjacent to that thermal energy heat release event attaining the temperature to go into thermal runaway themselves in a chain reaction. So the potting allows you to run tighter cell spacing while still passing the strictest of cell-to-cell propagation testing and validation testing for overcharge, nail penetration, crush, over temperature, and many more methods of inducing thermal runaway. It has excellent safety performance that to try to match it without potting requires impractical amounts of cell-to-cell spacing to have the similar safety results. And so you end up being overall smaller and lighter in these potted assemblies, despite it being counterintuitive that you would ever want to add something that has weight into your battery pack assembly.
For all the benefits, it seems like it's worth just even some napkin math to like see, oh, okay, here's how much weight I could save or how much you're adding.
Yep. And with very close cell spacings and, you can use potting displacement blocks, you could say. They could be injection molded thin outside wall perimeter blocks or, a foam block that's something closed cell so it doesn't absorb the potting but just displaces it to fill all the locations that you don't need the function of the potting. And so, the critical function of the potting is between cell to cell to prevent that impulse from thermal runaway spreading. And beyond that, its function is largely corrosion resistance, vibration mitigation, and chafing mitigation.
I guess we kind of covered like what processes are repeatable during manufacturing to ensure the design is protected. Basically potting.
Yeah, for the reason being that
there's challenges with potting though too.
Oh, there's lots of challenges with potting. It's its own devil to dance with as a manufacturing process. Being able to degas uniformly, being able to fill and set in a time that works with the takt time of the station. Fortunately, many of the pottings that we run are urethane family polymers, allowing us to set the curing rate to be only limited by your speed to get your assembly filled in the housing. So cure speed isn't usually a big obstacle, but it can be a messy, large volume on your line consuming process with many packs that are staged waiting to gel up in a queue. And so these things are their own disadvantages. But when you compare this with the disadvantages of, not only validating that you left with a hermetic seal, but ensuring that over the life of the product, you never develop a pinhole leak or weep in the assembly. Because if you do develop that pinhole leak or weep and you were relying on that envelope to prevent you from having a corrosion-induced failure, then those types of products usually end up being recalled, unfortunately.
Why do you think the industry is not talking about corrosion enough?
Right now, I think it's a sensitive topic because of product liabilities, shipped product, and when people find solutions, I think they like to try to wrap it in trade secrets. Of course, when people patent stuff, they've just given it to the world to freely use it because they shared the concept, so.
Well, I know that we have some solutions that we know work on different products, and it's not like we regularly go and advertise those.
Mm-hmm. It's corrosion costs something like just bridges and infrastructure, many billions of dollars a year, and it doesn't get a lot of discussion despite costing billions of dollars a year to bridges and infrastructure and things. But in the case of batteries in electric vehicles, I think it actually costs more than other infrastructure even. Or
at least has the potential to. Yeah, the more that it's ignored.
That's right. The more you ignore corrosion, the more expensive of a problem corrosion becomes.
I've seen a lot of corrosion issues based on stuff that I've learned from you and the industry, as far as I think that some failure is likely due to corrosion, but then when you read what the solution is or what they're saying the issue is, like, okay, you got to stop charging your vehicle or like something like that, is how do you actually identify corrosion? Is it just this like hidden thing in batteries that someone might overlook?
Well, what I mentioned is those isolation checks that I talked about early on. Those are really your keys. And once you find, a pack that has an isolation fault to chassis, those are your critical keys. You need to tear that pack down and do a forensic analysis to find the source of that pack. So if it's a large vehicle assembly and you don't know where the corrosion path is, then disassemble it one piece at a time, remeasuring chassis isolation with each component removed until you find, where your path was. And when you do find your path, examine it for the salt traces and salt residues that were in that path, because if it's failing your isolation test, there will be enough of an ionic path that you'll see salt formation, and you'll see perhaps even electrolysis pitting already formed.
That kind of leads into my next question of what kind of conditions are expected in a thermal event that would lead you to think it might be corrosion?
As a forensic investigation to determine if corrosion was present prior to the event, you'll have a layer of partially combusted organics and a soot covering surfaces, and so this is your trace for indicators for things that happened post-event. So as you remove this outer soot layer, you can begin to look for where you find salt formations, and some salt formations, they'll be underneath the soot as one indicator of which was there first, but you can also find further than the salt formations, you can find where it acted as an anode and consumed material with pitting. And not all battery events reach the same temperature, I guess is a nice way to put it. Some events undergo a thermitic decomposition of their cathode metal oxides, consuming the aluminum of the foil that they're coated onto, and consuming the aluminum as the fuel for that oxygen in a thermitic reaction. This leaves over 1600 degrees C molten nickel as a byproduct from it, and it's very difficult to get forensics evidence in the areas that this molten nickel had formed. However, you can look for the places that aren't as damaged to examine for what's underneath their outer soot layer and their outer deposits of condensates from the thermal runaway byproducts. And in a lot of cases, you can find clear evidence of situations that is, significant salt trails, salt tracing, and or electrolysis, metal pitting, and erosion that had to have occurred prior to the event. This is of course a signature of a corrosion-induced situation.
What are the safety considerations with dealing with effective protection from corrosion?
If you're lacking corrosion protection, your best case scenario is your product fails gracefully, and unfortunately, the worst case scenario, which is entirely too easy to occur, is that your corrosion progresses to a point that, say that you just fail the envelope that contains electrolyte in the pouch. So say you either eroded the steel of the cylindrical can until it breaches electrolyte, or say you corroded in from the edge of the aluminum in a pouch laminate until you've breached electrolyte. But once that assembly is flooded with electrolyte, now you have free, not only the carbonate solvents, but you have free lithium hexafluorophosphate ions, which of course decompose with water to make HF ions and other fluoride salts, many of which have melting points in the room temperature range. This is why if you do lose electrolyte containment, that is one step next to that is fire hazard risk, but you don't even need to be experiencing corrosion on the cells to have a molten salt bridge. Merely exposed bus bars that have a capillary path to wick liquids between them, contactor posts, fuse posts, all kinds of components that are part of the battery's power busing, but not part of the cells. If you develop the right or the wrong ionic conductivity from bridging those points with an aqueous path, just do condensates wicking between them, you can form a molten salt bridge through those processes as well, with no salt, no cell, and no electrolyte involved. Just the pack voltage being needed.
There's a test I know you like to show clients with 3 jars.
There is. It's where you put a large hole in the lid of one of the jars, canning jars with a screw type mason jar lid top. You put a large diameter hole in one jar. You put the tiniest pinprick you can make in another jar, and you leave one jar completely sealed. Don't damage the top on it. So you take this sealed canning jar, you put it in the chamber. You screw the lids down tight on all the jars. You run the same temperature and humidity profile, which matches many geographical regions of the U.S. at many seasonal times of year, where it simply warms up, decreasing in humidity throughout the day as the air heats, and then after the sun sets, the air temperature drops and the dew point rises as a function of the air not being able to hold as much humidity capacity as it cools until you condensate. And so you run this day-night cycle, and you can set your chamber up to perform what would have taken 24 hours. You can run it every hour, and that gives you 24 days per day in your chamber. And the interesting thing is the jar with the perfect hermetic gas tight seal stays dry inside. The jar with the large hole drilled in the top of it collects condensate and tends to reach an equilibrium point depending on the size of the hole drilled with them, where it's occasionally damp inside the jar. And the jar with the tiny pinprick on the lid accumulates with water. It never fills all the way up, but it'll fill 3/4 of the way up with water or more, which is kind of the example of why attempting to seal a pack is kind of like making a time delay aquarium for your battery, because you either perfectly seal or you allow egress and have everything coated and encapsulated so that it can natively handle being soaked all the time. And those are really the two operating regimes that are practical. The operating regime of starting sealed and assuming it'll maintain pinhole defect resilience to not accumulate with water and become a time delay aquarium. That's a very difficult challenge to ensure. It's a materials problem, even from the aspect that what happens if they scratch their pack, so you had corrosion resilience and protection on the housing of your pack, but what about when it's scratched by a tall rock, and anytime you have a system that if it develops a pinhole integrity defect, the product enters a dangerous failure condition, is a risky proposition.
There's another example you like to give about when talking about sealing packs and asking what happens when you drive up a mountain and drive down.
Yeah, a lot of folks tell me, their housing is sealed and they pass, IP whatever, and I can only chuckle because standards that use liquids are irrelevant from a validation perspective. Just because a liquid is so much larger and bound by its own surface tension to stay together, that it has virtually no intrusive power compared to a vapor or a gas. So in these situations, say it passes IP ratings for liquid protection ingress. Liquid is so much larger than vapors. You can pass submersion, you can pass spray, you can pass many tests involving liquid. And when you take that product to the top of a mountain, it will not maintain the manufacturer atmospheric pressure that it was assembled at. It will normalize its pressure. And when you drive it down from the top of the mountain, it doesn't maintain that artificially low pressure that was at the top of the mountain. It normalizes its pressure again. And so people often can recognize, when they go to the top of a mountain or when they come down from the top of a mountain, that the pack breathes and it had a respiration cycle where it egressed a bulk of molecules of gas inside the pack, and then it ingressed a bulk of molecules inside the pack. But the key factor to remember is you don't need to go to the top of a mountain and back. Every time it warms, the gas expanded and you lost molecules as though you were going up to the top of the mountain. And then every time it cools down again, it contracts and you drive the same pressure delta to egress vapors and gases, just like if you were coming down from the mountain. And this is why there's a huge divide between liquid validation, liquid ingress validation, and something that survives corrosion in the wild long term. They're almost unrelated, attributes to each other to pass.
Especially when it comes to automotive and batteries living outside.
Yep, salted road spray is a really
in the wild,
aggressive environment. Yep.
Thanks for listening to us talk about the importance of protecting your batteries from corrosion. We look forward to hearing from you if this is something you might be struggling with or think that there might be a potential issue with the products that you're working on, and we're here to help.